This is section 6.1, part 2. And we'll continue with another example of our linear motion. In this case, we have a cyclist riding down a long straight road with velocity v meters per minute. And our velocity equation, notice again this is already velocity, it's already s prime, is 400 minus 20t. And my first question, I'm going to modify this slightly. Let's figure out how far the cyclist travels during the first 10 minutes, please. So I'm going to start kind of like we started the last example. I'd like to graph this velocity equation. So this is t, this is v. This is just linear, so y-intercept of 400. And then it's just a line with a slope of negative 20, so it's going to slant down. Something like that. In fact, I can even tell that if t is 20, that would make the velocity 0, right? So 20 here is my t-intercept. Of course, you can also do this with a calculator graph. It was just a simple equation, so I kind of did this one mentally. All right, so in this case, we can see that our velocity is positive for times from 0 to 20. And then our velocity is going to be negative any time after that. All right, let's go back and try and answer our question now. How far does the cyclist travel during the first 10 minutes? How far would be a distance question. It doesn't ask where does it end up, it just wants to know how far it travels. And we know to find distance, we have to integrate, in this case, from 0 to 10, since it's the first 10 minutes, the absolute value of our velocity function. In this case, though, over the first 10 minutes in here, our velocity function is already positive, so I can basically just ignore those absolute values. They're not changing anything. I've got a positive velocity. So I'm just going to integrate as though the velocity wasn't even there, which is going to give me 400 times 10 minus 10 times 10 squared. Plugging in the 0 doesn't give me anything but 0, so I won't bother with that. 4,000 minus 1,000 is 3,000. So 3,000 meters traveled during those first 10 minutes. All right, part B. How far does the cyclist travel from time 10 minutes to time 25 minutes? Now we do have the issue of having a positive velocity for the first part of the trip and a negative velocity for the second. So I'm going to go ahead and set this up and say it would really be the integral from 10 to 25 of the absolute value of our velocity function again. But in order to evaluate this, at least by hand, I'm going to have to break that up into two integrals. From 10 to 20, we have a positive velocity. So I can just leave that 400 minus 20t the way it is. But then from 20 to 25, the velocity function is actually negative. So to take its absolute value, I would multiply it by negative 1. And that negative turns that other negative into a positive, so everything contributes to a positive distance. All right, integrating this, very similar. I would, of course, get 400t minus 10t squared, evaluated from 10 to 20. And let's see, that's going to be plus. Let's go ahead and distribute this negative 1. A negative 400t plus 10t squared, evaluated from 20 to 25. And I'll just trust you to plug in those values and evaluate your FTC there, your fundamental theorem of calculus. When I did this one over here, I got 1,000. And then this one, turned out to be 250. So my total distance was 1250. Now I know the problem didn't actually ask us to do it, but I'd like to just take a moment and sketch the picture of the cyclist's path again. We can put our information from the first two parts into doing that. And let's see here, if I start at 0, I'm going to say that for the first 10 minutes we go to the right, positive 3,000 because our velocity was positive. And then we actually go another 1,000 to the right, right? This one it was positive, this is to the right. This one came from the negative velocity, this one was to the left. So another 1,000 to the right before we turn around and come back 250 to the left. And we didn't do a displacement this time, but we can actually figure it out pretty easily. We came right total of 4,000 and went back left 250. So we're actually going to end here at 3,750. By the way, one thing I didn't put on our last diagram, I probably should have, was times. We started here at time equals 0. We turned around at time equal 20 when we stopped going to the right and started going to the left. So this turnaround point here is kind of important. I should probably label that time equal 20. And then our ending point here was actually time equal 25. And so you'll often include that time information in your diagram. And if you want to go back and do that for the previous example, I would recommend it. I simply forgot to do it when I was drawing. All right, our last question here. How far has the cyclist traveled when his velocity is 250 meters per minute? Well, we know the velocity, but we don't yet know the time. So let's go ahead and solve for time in our velocity equation. Remember, velocity was 400 minus 20t. And if I want that velocity to be 250, looks like 20t will be 150, and t is going to be 7.5. So that's the time when the velocity is 250. At this point, I can just say how far again. So this is once again a distance problem. My distance is just going to be the integral from 0 to 7.5 of the absolute value of my velocity function. And I really always recommend drawing these velocity equations. They help so much, or these velocity graphs. Again, you can see in the first 7.5 minutes, the velocity is already positive. We don't have to worry about the absolute values. We have a positive quantity anyway. So I'm just going to go ahead and call that 400t minus 10t squared from 0 to 7.5. Plug your 7.5 in, subtract what you get with 0, which is 0. And this one turns out to be 2437.5 meters. All right, so there's our linear motion problems. We're going to go ahead and we're going to continue to talk about linear motion, but we're going to introduce another couple of variables. We've mostly been talking about the velocity functions because everything hinged on velocity so far. But in the next couple of problems, we're also going to take a look at position functions and acceleration functions. So you've probably seen this before, but I just want to remind you. The relationship between position, velocity, and acceleration. If we have a position function, s of t, our velocity function is the first derivative, s prime, and the acceleration function is the derivative of velocity, which is also known as the second derivative of position. We can also work our way backwards. If we know the acceleration function to start with, the velocity function is simply the integral of the acceleration function. And once we know velocity, the position function is the integral of the velocity. So I always like to kind of think of it or remember it this way. To go from position to acceleration, this is the derivative direction. And to go from acceleration to position, this is the integral direction. All right, let's use that just a little bit in example 3. We have a block that hangs from a massless spring. By the way, I should probably mention, sometimes in order to use the amount of math we have to make some simplifying assumptions. This idea of a massless spring is obviously not realistic, but it's what we have to do to make things work so far. The more math you get, the more we can eliminate those unrealistic conditions, and we can include things like the mass of the spring or the air resistance, things like that. But for now, we have to simplify to the point that we have enough math to do it. So here we go. Our block hangs at rest from a massless spring at the origin. So that would be the position, s equals 0. At time 0, the block is pulled down 1/4 of a meter to its initial position. So notice this is time 0, s of 0, is equal to negative 1/4, down 1/4 of a meter. It's then released, and if you can imagine a block on a spring, it's going to bounce up and down, right? So just to sort of give us a feel for this, here's my spring. There's that little block that's hanging at rest. Before we do anything, it's at that position s equals 0. We're going to pull that block down 1/4 of a meter, let it go, and because of the spring, it's going to bounce back and forth, up and down. For our purposes, we're going to ignore air resistance, the mass of the spring, all of that, and we're going to have a very simple velocity equation. We're essentially going to assume that this is going to remain in perpetual motion. And its velocity function is given by v is equal to 1/4 sine t for all t greater than 0. We'll assume upward direction is positive. All right, we'd like to start by just finding a position function for our block for any t value bigger than 0. And since we were given the velocity function, right, we know our velocity here. Oops, saying t, get that in there. All we have to do is integrate to get our position function. So s is going to be the integral of v of t dt, or the integral of 1/4 sine t dt. Integral of sine is the opposite of cosine, so negative 1/4 cosine t. And of course, when we do an indefinite integral, we always get that constant of integration, the plus c. In order to solve for that constant of integration, you're going to use the initial position, this extra information that we were given here. We know that at time 0, s has to equal negative 1/4. So I'm just going to plug that information into my equation here. This is our s. S is negative 1/4. And that has to equal negative 1/4 cosine t. T is 0. Plus c. Cosine of 0 is 1. So in this particular case, c turns out to be 0. But it doesn't always, right? Just this particular case it does. So if I plug that in here, my final equation for s of t is just negative 1/4 cos t. All right, we'd like to graph that position function for the time interval 0 to 3 pi. And you can certainly use a calculator to do that if you want to. I'm just going to go ahead and sketch it. It's not a difficult graph to do, but if it's not one you're comfortable with, by all means, feel free to use a calculator. So let's see, cosine would normally start at 1, but it's multiplied by -1/4. So -1/4. There's that starting position. Again, not a surprise, right? The mass was pulled down 1/4 of a unit to start with. And then we're just going to go through here and show the first period of that cosine function would look like that. 1 full period, 0 to 2 pi. And then we got another half period here. And there we go. Position function from 0 to 3 pi. All right, I'm going to keep that graph handy because we'll use it to answer the next couple of questions. First of all, it says, when does the block move through the origin or the starting position for the first time? That, of course, would be right here, and that happens at t = pi/2 seconds. And then the next question, when does the block reach the highest point for the first time, and then also return to its lowest point? So highest point for the first time would be right there at t = pi. The position would be +1/4 or 1/4 of a is meters, whatever the distance, yeah, meters above equilibrium or above the origin. And then when does it return to its lowest point? That would be right here at t = 2 pi. It's down -1/4 of a meter or 1/4 of a meter below equilibrium again, or below the origin. All right, our last question, what are the displacement and distance traveled by the block over the time interval from 0 to 2 pi? All right, as we know, it's best to have our velocity function graphed before we start answering displacement and distance equations. So let's do that. Our velocity function was v is equal to 1/4 sine t. And again, you can either do this by hand or you can use a calculator. But our sine function would just start at 0, and it's going to have an amplitude of 1/4. So there's a quick little sketch. All right. First of all, a couple of predictions. Do you think you could tell me what the displacement should be without even doing any math? Look at what's happening here. We have a positive velocity for t values from 0 to pi. And then we have a negative velocity for t values from pi to 2 pi. But because of the symmetry, these positive velocities and these negative velocities are exact opposites. It seems to me that whatever ground we gain in the positive direction here, we would lose when our velocity is in the negative direction there, and we really ought to end up back at 0 again. So I would predict that our displacement should be 0. Let's calculate it, but I think we already know what's going to happen. So our displacement is the integral over our time interval, 0 to 2 pi, of the velocity function, 1/4 sine t dt. Notice I do not need absolute values because this is displacement, not distance. Integrating that is going to give me -1/4 cosine t from 0 to 2 pi would be -1/4 cosine 2 pi, subtract -1/4 cosine 0. Cosine 2 pi is 1, so -1/4 times 1 is -1/4, minus a negative is plus a fourth, and cosine 0 is 1 as well. So we do indeed get 0. Not surprisingly, it's exactly what we expected. All right, what about distance? Sorry, got my thing turned a little bit there. Now we have to integrate the absolute value of that velocity function. And of course it's positive from 0 to pi already. So from 0 to pi, I can just keep the 1/4 sine t dt. But from pi to 2 pi, we have a negative velocity. So we'll multiply that by -1 to turn it into a positive value. And so I would have the integral here, -1/4 cos t from 0 to pi. And minus a negative would make that a positive 1/4 cos t. From pi to 2 pi. And let's see here. I didn't have this one worked out in advance, so we'll do it. This would be a -1/4 cosine pi. Subtract a negative would be plus a fourth. Cosine 0 plus 1/4 cos 2 pi minus 1/4 cos pi and cosine of pi is -1, so that's positive a fourth. Cosine of 0 is 1, so plus a fourth there. Cosine of 2 pi is 1, so that's positive a fourth. And cosine of pi is -1, so negative times negative makes that a positive a fourth. And we have 4 1/4 for a total of 1 is our distance traveled. Several things I kind of wanted to point out to you here. First of all, notice that the distance with the positive velocity is a half, and then this distance here that came from where the velocity was actually negative is also a half. Again, the symmetry should make that kind of obvious. What happened on the top going upward here and what happened on the bottom going downward here are really the same distances, just in different directions. I'm also going to have you notice, if you come back over here to our position graph, right? Remember this was the position function. This is s. Notice what happened over this time interval from 0 to 2 pi. We started at -1/4. We went up to 0, up to positive a fourth, down to 0, and down to -1/4. So each of these is a quarter, right? Went up a fourth, down a fourth, down a fourth. That's a total of 4/4, or a distance of 1. So we can see a lot of things kind of coming together here. All right, we have one more example in this section, so I know this video is just getting a little bit long, but let's go ahead and squeeze it in so we don't have to make another one for 6.1. In example 4, given the acceleration function, e to the minus t, and a couple of initial conditions, v of 0 is 60 and s of 0 is 40, find the position and velocity functions of for this particular object. All right, so we know acceleration. If I integrate that, it will give me velocity. The integral of e to the minus t would be minus e to the minus t. And this is indefinite, so I would have that plus c, that constant of integration. And I'm going to go ahead and use my velocity initial condition. At time 0, velocity is supposed to be 60. So if I put 60 in for v, and 0 in for t, I can see that 60 is equal to -1 plus c, or c is 61. So my velocity equation is now minus e to the minus t plus that constant that turned out to be 61. Let's go on and find our position. Now that I know velocity, position will be the integral of the velocity function. And let's see, that's going to be a negative negative, so that'll turn back into a positive e to the minus t plus 61t. And again, plus a constant of integration. This is my s. And it's cut off of my picture, but you can look back at the top and see that we were given an initial condition for position. We were told that s of 0 equals 40. So at time 0, s will be 40. Now let's go ahead and plug that in. So 40 equals e to the 0 plus 61 times 0 plus c. That would be 1 plus 0 plus c. And it looks like c is 39. So my position equation, s of t, is e to the minus t plus 61t plus 39. All right, that brings us to the end of 6.1a, really. We'll continue with some other ideas that are presented in the second half of 6.1 in the next video.